Saxon's Trig, lesson 33. Has quite a few sections in it. It begins on page 233. It's about quadrilaterals, properties of parallelograms, types of parallelograms, conditions for parallelograms, and finally trapezoids. So in section A, it's basically a quick reminder of what is a quadrilateral. Well, it is a polygon that has four sides. No curves, that's what makes it a polygon, and it's going to have four sides. There are three kinds of four-sided shapes. One in which none of the sides are parallel. This one's harder for me to draw. I don't want that to look parallel, maybe something like that. Yeah, that'll work. So this does not have a special name. None of the sides are running parallel. If, however, you have two sides that do run parallel, so they're running the same gap between, and then we connect the ends. So one set of parallel sides is called a trapezoid. And then if we have two sets of parallel sides, so these two are parallel and then these two will be parallel. This set matches this set matches this set. Two sets of parallel sides is, and it's going to have that word parallel in it to try to help us. So parallelogram. And then parallelograms break down into squares, rectangles, and so on. So in part B, they say, let's talk about parallelograms, two sets of parallel sides. And we see a box, which means very important information. Properties of parallelograms, there are four. Both pairs of opposite sides are congruent. Well, I labeled that. This side is the same as this side is the same length as this side. Number two, both pairs of opposite angles are congruent. This angle will match this angle will match this angle. And three, the diagonals will bisect each other. So I'm going to draw another parallelogram here. The diagonals cutting from corner to corner, and I missed a little bit on that one, sorry. And it says that they bisect each other, meaning that this side, and it doesn't look that way here, it's not drawn exactly as a parallelogram should be. This side length should be identical to this one, and this side length will be identical to this one. They bisect each other. And then four, any pair of consecutive angles is supplementary. This angle and this angle together form 180. This angle and this angle form 180. These two form 180. These two combine together to be 180. Now that you know the rules, in example 1, it says, prove that the opposite sides of a parallelogram are congruent. And so then they do it in a formal proof, statement and reason. And they don't give you a picture. So it just says we're going to have to create a parallelogram and label it. So to match theirs, they did A, B, C, and D. So prove that the opposite sides are congruent. So maybe this side to this side is what we're trying to prove. So, oh, they did tell me that I have a parallelogram and it's labeled A, B, C, and D. That's my given. All right. And write a two-column proof to prove that B, we're going to have to do two of them. Maybe I'll do two little circles. So BC is congruent to AD and AB is congruent to DC. Now we have them all marked. Okay, so we begin with our given, and I can't work with this unless I have triangles. So I need to create a triangle. So they drew in a line AC. So step 2 is going to be draw segment AC. Oh, they actually put that in their given, which is kind of funny. They said it's a parallelogram with diagonal AC. I would just say my reason here is I constructed it. All right, so now it has its diagonal, and I have two triangles. I see that the AC that I just drew in is congruent to itself because it's a shared side in both triangles. So reflexive or identity, however you wish to label that one. Now I have one part. Can I find any other parts? I know from the earlier rules in a parallelogram that if this side is parallel to this side, then AC is a transversal. Oh, yes, I can use that for alternate interiors. So angle CAB, I think we'll go that way, is congruent to, so that's this one that I just did. So its alternate is this one. So that would be angle, and I started with C before, I did CAB. So we want to do DCA. I think that's right. Did I flip that? That's what I was debating. C is the one opposite the one I'm trying to state. So A is the one, oh, I did flip it. ACD, okay. And they are the same because they are alternate interior angles. All right, another step. So I have an angle and a side. We can do the other angle. I could have done that in step 4, to be honest. Let's do that. Let's say that angle, so now we're doing the 2, ACB is congruent to angle, okay, so I did the one opposite the 2, so that would be CAP, and same reason, alternate interior angles, that's why I could write it in the same step. Now I can state that the 2 triangles are congruent, so triangle ABC is congruent to triangle CAP. Why can I say that? Because I showed angle, side, angle. I'll get them in an order. And then I want to show that this side is matching with this side. So I can say that AB is congruent to CP. Why? CP, CTC, corresponding parts of congruent triangles are congruent. How about the other 2 sides? Can I list those for the same reason? Yes, I can. So BC is congruent to AP, and that is, I believe, I didn't write them in the same order they wanted, did I? Just a second, BC, A, oh, that's a D, not a P. My goodness gracious. Try that again. Same problem here. I use that as a P, not a D. That's because I was not super clear when I did that. These other places where I said cap, that's a CAD. That's a D too. Yeah. Now let's make sure I wrote them exactly as they wanted them. BC to AD, AB to DC. To match what they wanted, I would actually then write that as DC. I'm getting picky there, but I do want you to have the right steps and not like flip-flop things around. Section C now talks about the types of parallelograms. So when I was doing this, I said you've got some special ones, rectangles, squares, and rhombuses. To try to help organize this, they show you a Venn diagram. And so a rectangle is something where obviously both sets of sides are parallel. That's why it's a parallelogram, and its corners are 90 degrees. That's great. And then on this side, I have a rhombus, and it has 2 sets of parallel sides. They're parallel, so therefore it's a parallelogram, but these corners are not 90, so they are rhombuses. And then this one was rectangle. And then sharing a characteristic with them is a special kind of rectangle is your square. All sides are parallel. It does have the 90-degree corners, and all 4 of the sides are the same length. And I didn't say that about a rhombus. All 4 of these sides share a length, and so that's why a square is a combination of the rectangle and the rhombus. So now that we understand what the special types of parallelograms are, on page 235, they start giving you some properties of these. So what do we know about a rectangle? Well, step 1, all properties of the parallelograms apply. So that first box where we walk through all of these pieces, they apply to a rectangle. What's new for a rectangle? All angles are right angles, and I said that when I drew the Venn diagram for you. And then 3, the diagonals are, now before they bisected each other. This one is the diagonals are congruent. So it still has to bisect, as they said, but this length has to equal this length. That's that new rule. Now, what are the properties for a rhombus? Well, we know that all sides are the same length. So all properties of the parallelogram apply. Okay, so everything we had from before. All sides are congruent. That's the one I just did. The diagonals are, okay, so not only do they bisect each other, they are, it says, perpendicular. So they form 90 degrees where they cross. The diagonals bisect the angles whose vertices they connect. So the other rule is that this diagonal cuts this angle into equal parts and that angle into equal parts. The intersecting diagonals divide the rhombus into 4 congruent right triangles. So this is a right triangle, this has to be right, this has to be right, and that has to be right. There are 4 of them. That's 4 right triangles, and they are all the same size and shape, therefore they're congruent. Okay, now we get more specific with the square. All the same rules that apply to rectangles apply to a square. All the rules that apply to a rhombus apply to the square. And its new one is the diagonals form 4 congruent, that's the same as before, 4 congruent isosceles right triangles, because this side and this side have to be the same length to match those earlier rules, and this one and this one. And so if you have 2 sides of this triangle that are the same, it's called isosceles. This one has 2 the same isosceles. So they have 4 congruent isosceles right triangles. Okay, we've gone through all of those rules. Example 2. The diagonals of a certain parallelogram are of equal length. Which of the following could the parallelogram be? And it says A is a rectangle, B is a square, C is a rhombus. So it's talking about the diagonals, and it said, did I say equal or unequal? It says unequal. I'm not sure how I read that the first time. So starting with rectangles, we knew that the diagonals had to be the same. In the rhombus, were they sharing that same? No, we did not talk, we did not say the same about the rhombus. And if the rectangle has it, we said the square had to have that same rule. So the only one that works for the diagonals to be of differing lengths is C, the rhombus. All right, example 3. The diagonals of a certain parallelogram are not perpendicular. So we said these had to be perpendicular and the square had to be perpendicular. So the same choices are rectangle, rhombus, and square. Which of the following could the parallelogram be? Well, we've just thrown these out, so that only leaves us with rectangular, which was A. Okay, part D goes back to giving us more information. So conditions for parallelograms, and they summarize them in their very important boxes. So conditions for a quadrilateral 4-sided shape to be a parallelogram. A quadrilateral is a parallelogram if any of the following conditions are satisfied. So it is basically now giving you all of the rules that we just said in reverse. Both pairs of opposite sides of the quadrilateral are congruent. So if the 2 sides are the same, then we know we have a parallelogram. If one pair of the opposite sides has the matching angles, we know we have a parallelogram. If the diagonals of the quadrilateral bisect each other, you get the idea here that these are just the rules in reverse. Both pairs of opposite angles of the quadrilaterals are congruent. Okay, then we also have the rules that work for them to be a rectangle. If a quadrilateral is a parallelogram and its diagonals are congruent, then it must be a rectangle. And all 4 angles of the quadrilateral are right angles. The quadrilateral is a rectangle. I'll just finish reading them, but you've got the idea. Conditions for quadrilateral to be a rhombus. If a quadrilateral is a parallelogram and either of the diagonals bisects the angles whose vertices it connects, then it's a rhombus. If the diagonals of the quadrilateral are perpendicular bisectors of each other, then the quadrilateral is a rhombus. Okay, now we get into example 4. At the top of 237, given a parallelogram whose diagonals are congruent, the same, which of the following must be true? All right, so I have diagonals. So I don't know what my shape is, but I have diagonals that are the same length. That's what it's giving me. In A, it says, am I forced to have all 4 sides the same length? No, because in a rectangle, I have diagonals that are the same length. B, the diagonals are perpendicular bisectors of each other. The diagonals are perpendicular bisectors of each other if they are the same length. Possibly. Let's read C. All 4 angles in the parallelogram are right angles. Ooh, do I know for sure that I'm forming 90 degrees here? I do not. So B, by default, given those choices, is the answer. Oh, wait a second. Did I just misread that? Triple check myself. The diagonals are perpendicular bisectors of each other. Can I guarantee that's 90? No, See again, all 4 angles of the parallelogram are right angles. Oh, my goodness gracious. Yes, because in order for them to be congruent, it has to be a rectangular shape, which means yes, the corners have to be 90. Yes, the answer is C. Goodness. Section E, trapezoids. All right, so now we're going back to talking about one set of parallel sides. They give you some other terminology here. On a trapezoid, you have legs, and they are the bases. So the ones that are parallel are your bases, and we call those the legs. And then we can have a height or a median that's drawn in. And the other word for height is altitude. Oh, okay, yeah. I see what they're trying to give you here. A median is the part that connects in the middle between them. It can have one height, and it can have multiple heights. And that one, I'm not going to draw that one, but at the bottom of page 237, it gives you the properties for the trapezoid. The area of a trapezoid, the area for this whole shape, equals 1/2 the product, that's multiplying, of the lengths of the altitude, the height, and the sum of the lengths of the bases or the legs. So base 1 plus base 2. That's the first property. They want you to prove in an example why that works. Number 2 says the median, the line here, of a trapezoid is parallel to its bases. So the median must be parallel to these, and its length is 1/2 the sum of the bases. That's the median. And this one was the area. Okay, so those are your properties given to you in advance. And they switch gears on page 238, and they talk about an isosceles trapezoid. So an isosceles trapezoid is going to have equal sides. All right, so then they clarify the terminology: lower base angles and upper base angles. Lower base angles, upper base angles. Now, what are the properties if it is an isosceles trapezoid? The lower base angles must be congruent, equal. This angle has to match this angle. The upper base angles are congruent. This angle must match this angle. The diagonals are congruent, so connecting here to here must be the same length. Any lower base angle is supplementary to an upper base angle. This one plus this one must be 180, just like our rule from before with our parallelograms. Same thing applies. This one plus this one will equal 180, or those two will equal 180. Now we've done the properties. Example 5, derive the general formula for the area, I said they were going to make us do that, in the trapezoid using the figure shown. This side is parallel to, I didn't want to make them look, this one's supposed to be, this one's way more out. Okay, that looks a little bit more like their picture. This line is parallel to this line, and they're calling this base 1. Oh, need the little arrows to indicate parallel, and they're calling this one base 2. And over here, they've marked that this would be the height of the shape. So when they want me to derive this as working, I'm not going to do a formal proof for this derive. It's just a quick sketch. So if I split this into two triangles, I know that the area for a triangle is half base times height. The height is obviously here, and this is base 2. This one is also half base times height. Is that the same height? Oh, yes. And this is actually base 1. So if I put that together, the area for the whole shape is half base 2, 1/2 height base 2 plus 1/2 height base 1. And then if I pull it out so that it matches this look, they both share a half, they both share the h, and then that leaves me base 2 plus base 1, giving me the area. Example 6. The figure shown is a trapezoid whose area is 175 centimeters squared. It has a very short top. This one's very long. And we'll connect that to be parallel. My height is listed over here at 10. And this one is x, this one is 2x plus 8. And it said the figure shown has an area of 175 centimeters squared. Find the x. So how do I find the area of this whole shape? Well, we just said it's a half times the height of 10 times the bases added together. So x plus 2x plus 8, that's the area formula. And how much did that equal? 175. Half of 10 is 5. X plus 2x is 3x plus 8 equals the 175. Distribute 5 times 3, 15. 5 times 8, 40 equals 175. 15x minus 40 to move it to the other side. 135. Divide by 15. X is 9. Yep, just doing a double check of that math. And it says dimensions are in centimeters, find x. So x is 9 centimeters is what they're looking for the answer. Example 7. In the figure shown, EF, all right, so this one is more with those the same. So the median is listed as 4x plus 1. The top is 2x plus 2. The bottom is 7x minus 2. They have some letters labeled around there, but it's basically saying this middle one, EF, is the median of the overall trapezoid. Find x. So what did we know about the median? It was half of the bases added together. So 2x plus 2. Oh, didn't mean to put a parenthesis there. 2x plus 2 plus 7x minus 2 equals the median, which is 4x plus 1. I'm going to go ahead and combine like terms in this parenthesis first and then deal with the half. So 2x plus 7x is 9x. 2 minus 2, oh good, that's gone away, equals 4x plus 1. Now we'll distribute here. So this is 9/2 x equals 4x plus 1. My x terms need to go together. and I want the number on the other side since I'm solving for x. So I'm going to minus 4x. 9/2 minus 4 is what I'm trying to do. Common denominator of 2, that's going to change that to 8. 9 minus 8 is 1, so I have 1/2 x equals 1, because that's dropping down. When I divide the fraction to remove it, flip and multiply, so x equals 1 times 2 is basically 2. And they wanted me to solve for what x was. Final example, then we're done.